section, we're going to talk about how to solve compound inequalities graphically. And in particular, we're still going to focus on all three types of compound inequalities. The first type being the three-part inequality or triple inequality. The second type being the inequalities connected by and lastly, we're going to go over how to solve compound inequalities graphically while they're connected by the word or. So first of all, we're going to look at the triple inequality or three-part inequality. And what that means is that when we look at the three-part inequality, we always see, first of all, there are three parts involved. And this is really just a more concise way to write some part of the inequalities that are connected by and we say it's more concise because we can really consider this as one expression involving variable being restricted on both ends. For example, in our example 1, if we're looking at this particular inequality, we're really looking at the one side, negative 15 is less than negative 3 minus 4 over 5x. And in addition to that, we also need to have that restriction negative 3 minus 4 over 5x is less than or equal to 5. So that's the other side of the restriction. And if I want to write it to be inequalities connected by and, I can totally do this. And what's nice about the triple inequality is when the variable expression involved are exactly the same, we can just shorten this expression into a three-part inequality. And the first type of problem we're going to look at is how to solve this kind of inequality graphically. And in order to solve it graphically, the first thing we want to do is to carefully draw the graph. And in this section, we're going to focus on drawing linear equations by hand without any technology. And that really trains us to kind of go over the knowledge on how to properly scale the axes and label everything. And in order to solve the inequality, we're going to try to find where the intersections are on the graph that would be helpful for us to find the solution. And lastly, to answer the question, we're going to write the solution in interval and set notation. So before we start, the first thing we want to do is to see how we can kind of scale the x and y axes over here. And first of all, to solve our inequalities, the key word you might have already caught up is the intersections over here. So we say that graphically, if we are solving for any inequality, we're really paying attention to the intersections of the linear equations we have. And this technically extends to any type of graph or any type of function. So wherever the graphs of multiple equations intersect with each other, that's where we can go ahead and find the solutions for our inequalities or equations over here. And now if we want to look at this particular example, I'm going to go ahead and try to think about the restrictions I have over here. Here I know that our expression is bounded by negative 15 and 5. And just to make things a little bit easier to express and keep track of, I'm going to just let my expression y1 to be equal to negative 3 minus 4 over 5x, which is a middle part of our three-part inequality. And when I label it this way, that means I'm going to go ahead and graph this equation on the coordinate plane. And in addition, I know that y1 is bounded between negative 15 and 5. So I can also just let y2 be equal to negative 15 and y3 be equal to 5. And that way we can be clear that these restrictions are referring to the y values over here. That's what we're paying attention to. And with this scale of y value, I know I need to go all the way down to negative 15 and all the way up to 5. These numbers all need to fit on my y-axis. So because of that, I'm going to look at the scale with my limited space. I decide to probably go up by 2 every time if I go up each tick mark. So I can have 2, 4, 6, etc. And similarly, that scale should be used on the negative side as well, until I get to negative 15. So I'm going to label some of the tick marks just to make it easier for me to find the points or count the points later on over here. And here I have negative 16. I know that's low enough because negative 15 is slightly above that. And now going back to the x-axis, what we can do is think about what scale we can use for that. And here I have a little bit more space for the x-axis. So what I can do over here is I'm going to just go up by 1 every time when I go through each tick mark. And just for simplicity reason, I'm going to label every 5 points over here, or every 5 tick marks, and we can see why that can be helpful in a minute. And I think I get to exactly negative 10 over here. So that's what we have to start with. And the reason I like to kind of label some of the tick marks only is so that I'm not overcrowding this entire coordinate plane with a ton of numbers. That makes things a little bit hard to see later on. And now going back to our equations over here. The first one we have is a linear equation, and this is already in the slope-intercept form. And as a quick reminder, for slope-intercept form, that means whatever number or coefficient is in front of x, that's going to be the slope of our line. And in this case, we have a negative slope for our line. That means when you draw the line, it should look like it's going downhill. That's a general shape you should be aiming for later on. And then we have that negative 3. That tells me the y-coordinate of the y-intercept. And for it to be y-intercept, that means it's on the y-axis, meaning x-coordinate of that point is going to be 0, and the y-coordinate is indicated by b over here. So this is going to be our y-intercept in this case. So with the y-intercept, that's going to be the starting point I use in order to graph the line. So 0, negative 3 will be right over here because each tick mark is 2, so it's just 1.5 tick marks below the origin over here. And then we have the slope is negative 4 over 5. That means every time I go down 4, meaning if the rise is negative 4, I should go over to the right by 5. So you can see that's where labeling every 5 is particularly helpful as well. And if we go down by 4, that starting from 0, negative 3, we would go 1, 2 boxes down and 5 units to the right over here. Be extra careful when you're using different scales for x and y axes like I am over here, because it's easy to kind of just count the boxes without thinking too much. And then we can keep going and do one more on this direction. So we'd have 4 down and 5 over. That would lead me right over here. And similarly, on the left side of the y-axis, I can do the same thing. In this case, I'm going up by 4 every time, so I need to go the negative direction on x. So that means I go left by 5. Every time I go up by 4, that would lead me over here. If it helps, definitely feel free to label more of the numbers on the axes to kind of help you keep track of how big of a jump you're doing every time. And similarly, I'm going up by 4 here and going to the left by 5 in this case. And now I have 5 points, and generally I recommend doing at least 3 points just so you can draw a long line that's actually straight and going through all the key points. And because we're solving things graphically, it's even more important for us to graph everything more exactly over here. Here actually I noticed that as I am saying we need to be extra careful with it, I skipped a box over here, or skipped by 2 over here. So it should really lead us to this point. For negative 5, it should have the y coordinate being positive 1, and for x equals negative 10, it should have the y coordinate being positive 5. Feel free to label the points to kind of help you keep track of this process as well, in addition to what I am doing over here. And once you have the points, we can go ahead and connect them. And whenever you can't connect them with one straight line, like what happened to me, you know something's probably off. That's a good checking process to have. And here I connected all the dots, and they can technically extend both sides over here. That's our y1. And for y2 and y3, they're going to be much easier to graph because we have y2 and y3 equal to some constant values. And when that happens, we just have a horizontal line over here. So if I have y3 equal to 5, that would be right over here in this case. I'm going to use a green line for that. And if I only have the restriction for y3 equals 5, or if I only have the restriction related to 5, then the only thing I need to do is to find the intersection of my red line y1 compared to the line y2 over here and see where they intersect. And for that particular restriction, we can see they intersected right over here. And when I look at this point, we can read the coordinates for here, which is negative 10, comma 5 over here. And whenever we're solving an equation, that tells me that I need to solve for the variable x, just like we did when we solve inequalities or equations. Symbolically, we were solving for x even though we were considering the restrictions regarding y. So with that information, when I have that coordinates for x and y both, all I really want to focus on is the x coordinate. That's going to help me find the solution over here. And in order for the y value to stay below 5, that's a part of the line that's going to be going towards the right over here, because we can see as the red line keeps extending further to the left, it's going to go above 5. That's not what we want. We want it to stay below 5, and that's a part of the red line we can actually see that fits in the coordinate plane. And for the same argument, for the other restriction, we have y2 equals negative 15, or yeah, I mislabeled this. This should be y3, and y2 is negative 15. So we would go ahead and draw the line for negative 15 over here. And that's the other side of the restriction I get in this process. Again, they can be extended both ways over here. And to find the intersection, I have it right on here. And that would give me, if we count it, I think it's at 15 over here. So the coordinates is 15, negative 15 over here. And that's how we find the other intersection. And for that intersection, for the same argument, I still want to look for the x value that's related to that. That's how we find the solution based on the intersection. Now if I want to find the part of the y1, negative 3 minus 4 over 5x, that's between negative 15 and 5, that really tells me that I'm focusing on this little section of the red line over here. That's a part that meets the restriction. But in particular, we don't want it to include negative 15 over here. So what we want to do is when we write the solution, we want to exclude the end point of positive 15. And because we have this entire interval, we can write out the solution in set notation first. And for the set notation, we can say we are looking at x while x is anywhere between negative 10 and 15 over here. And still we're going from the smallest value to the largest value regarding x. And here for negative 10, or for the restriction of y equals 5, we want to include negative 10 as part of the solution. And for the same argument on the y2 end, or the negative 15 as a restriction, we don't want to include that endpoint, so we are going to exclude that negative 15 over here in our solution. And another thing you could do over here when you're drawing the restriction, as we're not including negative 15 as part of the solution, is instead of drawing a straight line like I did initially, you could draw a dotted line over here. That way, that's another reminder for you that instead of including that endpoint, we're going to use a dotted line to say whichever is indicated by that part of the restriction, that's going to be excluded in terms of the endpoint. And similarly for interval solution, or interval notation for the solution, we're going from negative 10 inclusive all the way to 15, excluding 15 over here. And that's how we solve the three-part inequality graphically, using the coordinate plane and the graphing skills we had from before.